So now I'm talking about the second law of thermodynamics. The second law of thermodynamics states that heat will transfer from a hot object to a cold object, and that transfer is spontaneous, meaning that there's no need for motivation. We don't have to motivate heat to transfer from a hot object to a cold object. It'll do it on its own. It also states that heat will not transfer from a cold object to a hot object, that it's a one-way trip. Okay, so if we remember, we were talking about thermal equilibrium. We were talking about conservation of energy. So the zeroth law saying that everything is trying to achieve thermal equilibrium. Everything's trying to achieve the same temperature. The second law says that if the system is a closed system, that the energy in that system is constant, and only the energy of the system will only change if there's an external force or an external energy that's going into the system, that's delivering energy into the system. And one method of delivering energy is this term heat. Now the heat is just the way in which we can transfer energy from one form to another, and it's usually to be honest, I've never seen it expressed any other way than to talk about the delivery of thermal energy from one source to another. You can argue, especially when talking about radiation, that radiation is not necessarily the word thermal, but for all intents and purposes, consider the word heat to be talking about the transfer of thermal energy from one object to another. So, and then now we're talking about this second law of thermodynamics, where everything is trying to achieve this, or not everything's trying to achieve this, but heat will transfer, will automatically start moving from its original source to a colder source, spontaneously. There's no motivation for it. The methods of transfer are up there: conduction, convection, and radiation. So these are the ways in which heat is transferred from one object to another object. The first one, conduction. Conduction is a pretty simple way of understanding things. Conduction is the process of direct contact between two objects. Okay? So this being a hot object, this being cold. Now, if we're talking about hot, and if you remember when we talk about hot, we're talking about the kinetic energy that object has. So that means that particles inside this hot object are in motion. They're moving around randomly, according to the ideal gas law, just moving around randomly. And over here we have some slow-moving objects not really doing much. Well, when these hot objects collide with these slow objects gain kinetic energy. They start moving a little bit faster. Okay? So the process of conduction is saying we'll have direct contact so that these hot particles over here with all this kinetic energy can strike these cold particles directly and deliver energy to them. Okay? That's the process of conduction. Now, convection is similar to that, but convection requires a middleman. The bad thing about sidewalk chalk is that you can't really erase it very well. So again, we got a hot object here. We have a cold object here, and now there's a space in between. Okay? And that space in between is occupied by a fluid. Now, fluids, you've got to be careful about. Fluids are not necessarily talking only about liquids. Gases fill in the fluid category too. So it's anything that has this free motion of particles. Particles are allowed to move freely in that area. Okay? So that's a fluid. So it's not only liquids, it's gases. So when somebody's talking about fluids, they're talking about something that has free moving particles. And that is two things. It could be three if we go back to our states of matter. Plasma can be viewed as a fluid too, because it's a free moving particle. Okay? Hot space filled with a fluid, cold. So now in this case, you have these hot particles that are still moving around randomly inside this container. They strike the fluid particles that are in this gap in between, and gives energy to the fluid particles. Those fluid particles are now moving randomly into the space around there, eventually striking the cold, heating up the cold. Okay? So the second method, convection, is the use of a medium. It has a middleman in the process. So the hot particles strike the fluid particles. Those fluid particles are allowed to move freely. They float over. They strike the cold object. The cold object gets the energy from the hot particles. So it's kind of a middleman process. Now, in cooking, there is a conduction way of cooking and there is a convection way of cooking. I guess I should talk about cooking after I'm done with radiation. Okay, cool. So that is convection. Now, lastly, let's talk about radiation. Hopefully, this, for the most part, it's kind of erasing. So radiation is actually a pretty common way of delivering energy. Most of the energy that we get here on the Earth is a result of radiation. Radiation is the delivery of heat from an object, but not using the two methods in between. Using radiation, and in particular using, electromagnetic radiation, light. So you have a hot object. In this case, my hot object is a round object, and that round object we probably would like to call the sun. Okay? And that delivers all of these pieces of light, these small pockets of light. Okay? And we call those small pockets of light photons. That's basically the definition of a photon, is a small packet of light, okay, that are being ejected from the system. Now, it's light. It has energy associated with it. There is energy there. Depending on the frequency of light is actually their amount of energy. Certain light that have really, really long wavelengths are low energy, and other light that have very short wavelengths have less energy. But that's still energy. So it's still being able to deliver energy from one object to another object. Okay? Now, see, that's kind of why radiation is a little different than these two, and why I'm saying, well, radiation, we throw it into the thermal category. Isn't it's not a hot particle moving back and forth. Instead, it's a packet of light. That's our method of energy delivery. So all this energy goes out. It goes over here to a cold object. Once again, it's a round object. I can kind of imagine what that would be. We'll call that round object Earth. And all this light comes in here and heats up that cold object. It's energy being delivered. Now, you can say that that light strikes the atmosphere and heats up the atmosphere, which then heats up the surface of the Earth. But in some cases, that light does not strike the atmosphere and just continues to go straight through. Okay? It goes pew through the atmosphere and strikes the Earth, heating up the Earth itself. As a matter of fact, talking about evaporation, when you talk about snow cover, the reason why snow stays around so long is that it reflects a great deal of this radiation. Okay, so it has to rely strictly on convection and convection and conduction. To a point. I mean, there is still energy being delivered to that snow, but that white surface allows light to come in and bounce back off without delivering its energy into the snow. So when we had the Ice Age, when we were talking about a great portion of the planet being covered in snow, you had light come in, strike the surface of that snow, and then come right back out. So we were experiencing the same amount of energy per cubic meter on the surface of the Earth. But it wasn't being retained. It wasn't being held in by the bulk mass of the Earth. It was striking and then bouncing back out. Okay? So that's radiation. Now, radiation isn't only a method of delivering energy in vacuums. I mean, the distance from the sun and the earth is nothing but a vacuum. There's nothing in between there. There's a few particles, but not very many. And there's a few planets, but hopefully we're not going to get conduction at delivery conduction thermal or conduction at experience conduction by other planets, because that would be a really, really bad thing. But most of the energy is being delivered via the radiation. Now, talking about cooking, I wanted to talk about cooking on this one. Talking about cooking, conduction is pretty common. If you think about conduction, a deck oven is a perfect example of a conduction oven. Even a heating coil to a point. If you're cooking directly from like a skillet, like you're frying an egg, that conduction, the heat is being delivered to the pan. The pan is heating up, and then eventually that pan is going straight into that egg. That's conduction, conduction, conduction. Now, if you were poaching an egg, if you were boiling that egg, you have heat being delivered to the pan, but the pan is then delivering energy into a fluid, and that fluid is then delivering energy into that egg. So you're looking at conduction, convection, okay? And then there's also what's called a convection oven. And a convection oven, all that works is they heat up air and they cycle that air into a system. I mean, your typical oven is a convection oven in a sense, in that the burners are on the very bottom, and it requires there to be air into the oven, and then you heat up that air, and that air bakes whatever is inside of your oven. So it still relies on convection. Both of those are convection ovens. The word convection actually has a fan that, cycles the air. So the air is moving into the oven. That way the oven is equally heated. The thermal energy is being distributed evenly inside that pocket of air, where inside of an oven, typically really close to the burner, is really hot, and as you go further up, it's colder, where a convection oven doesn't have that same process. Now, for cooking, radiation, microwave ovens are a perfect example of radiation. Even though you're in an atmosphere, you're in an air, radiation is still happening. It's delivering high energy photons directly into your food. And it turns out those high energy photons are sympathetic to the water molecules in your food, and it heats up those water molecules. Those water molecules move around really fast. Here's your water molecule, here's your photon, comes in, boom, starts moving those water molecules. Well, that's temperature. That's kinetic energy. That molecule is moving. So that's a representation of temperature. You're heating up your food. Okay? Cool? So that is thermodynamics, second law. Conduction, convection, and radiation.